Our planet is an extraordinary library of stories, written not in ink but in stone. And perhaps the most detailed and revealing chapters are found within the layers of its crust. Today, we're exploring the fascinating world of sedimentary rocks. These are not just inert stones. They are the archives of deep time, holding clues to ancient oceans, long-vanished mountains, and the very first stirrings of life. Each grain, each layer is a word in a story that stretches back millions, even billions of years, a narrative of constant change, of destruction and creation. To understand this grand story, we must first learn its language. Sedimentary rocks, in all their varied forms, are the product of surface processes, the relentless work of wind, water, and ice. They are born from the remnants of what came before, painstakingly assembled over immense timescales. It is a process of accumulation, of slow, patient layering that builds the world we see around us. In our journey today, we will uncover the three great families of these remarkable storytellers. We will look at the rocks formed from the shattered fragments of older landscapes, those born from chemical precipitation in ancient seas, and finally, those created from the very fabric of life itself. Each type tells a unique tale, a different chapter in the epic biography of our world. So, let us begin our exploration into these chronicles of the Earth. Our story begins with the most common family of sedimentary rocks, the clastics. Their name comes from the Greek word klastos, meaning broken, and that is precisely what they are, a mosaic of broken pieces. Imagine a towering mountain range, ancient and immense. For millions of years, it stands against the sky, but it is not immortal. The patient forces of erosion, the freezing and thawing of water, the scouring of wind, the relentless flow of rivers are constantly at work, breaking it down, grain by tiny grain. These fragments, from large boulders to the finest specks of silt, are the raw materials of a new creation. Once liberated from their parent rock, these fragments, now called clasts or sediment, begin a journey. They are carried away by the powerful currents of rivers, tumbled along the beds of streams, or swept across deserts by the wind. This journey is not a gentle one. As the fragments travel, they are weathered further, their sharp edges rounded and smoothed. They collide with one another, becoming smaller and more refined, sorted by the energy of the water or wind that carries them. The largest, heaviest pebbles are dropped first, while the lightest grains of sand and silt can travel for hundreds, even thousands of miles. Eventually, this journey must end. As a river slows upon meeting a lake or the vast expanse of the ocean, it loses its energy. It can no longer carry its load of sediment. The fragments begin to settle, drifting down through the water column to rest on the floor below. Year after year, century after century, flood after flood, new layers of sediment are deposited on top of the old. This process of deposition builds up a thick blanket of loose material, a graveyard of a mountain range that once stood tall. The story of the rock is now entering its next phase. The sheer weight of the overlying layers creates immense pressure on the sediment buried deep below. This is compaction. The water that once filled the spaces between the grains is squeezed out, and the fragments are forced closer and closer together, interlocking like pieces of a puzzle. It is a process of incredible force, transforming a loose bed of sand or mud into something much denser, something beginning to resemble solid rock. But one final, crucial step remains in this remarkable transformation. Flowing through the now compacted sediment are groundwaters rich in dissolved minerals such as silica, calcite, or iron oxides. As this water percolates through the tiny remaining pore spaces, these minerals begin to precipitate out, acting as a natural cement. This process, known as cementation, is the glue that binds the individual clasts together. It is the final act of creation, locking the fragments into a solid, cohesive mass. What was once a collection of loose grains has now become a single unified entity, a clastic sedimentary rock. And so, a new rock is born from the ashes of the old. A sandstone might tell of a vast, ancient desert or a long-forgotten beach. A conglomerate with its coarse, rounded pebbles speaks of a powerful, fast-flowing river, and a fine-grained shale whispers of the still, quiet depths of an ancient sea or a tranquil lake. Each one is a time capsule, a physical record of a specific environment on a younger Earth, waiting for us to read its fragmented history. We now turn our attention to a different kind of creation, one that occurs not through the breaking of rock, but through the chemistry of water itself. This is the realm of chemical sedimentary rocks. Here, our story begins not on a mountaintop, but within a body of water, a shallow sea, a vast lake, or a restricted lagoon. This water is not pure, it is a solution, a soup of dissolved minerals carried from the land by rivers or leached from the seafloor by hydrothermal vents. Under the right conditions, this invisible dissolved world can become solid. The process is one of precipitation. Imagine a vast shallow sea in a hot, arid climate. The sun beats down relentlessly, and water evaporates from the surface faster than it can be replaced by rainfall or rivers. As the volume of water decreases, the concentration of the dissolved minerals within it increases dramatically. The water becomes supersaturated, a point at which it can no longer hold all of its dissolved load. The minerals have nowhere to go, and so they begin to crystallize, falling out of the solution and settling on the seafloor. This process can create vast, thick beds of a single mineral. Rock salt or halite forms in this way, leaving behind a record of an ancient, evaporated sea. These salt flats can be immense, stretching for hundreds of square miles, their crystalline surfaces gleaming under the sun. Another mineral that forms in this way is gypsum. These rocks, known as evaporites, are direct evidence of past climates, telling a story of intense heat and dryness in a specific location on Earth's surface, a geological snapshot of a long-gone environment. But evaporation is not the only trigger for chemical precipitation. Changes in temperature or chemistry can also cause minerals to fall out of solution. In some caves, for example, groundwater rich in dissolved calcium carbonate drips from the ceiling. As the water comes into contact with the air, it releases carbon dioxide, changing its chemistry and causing the calcium carbonate to precipitate. Over thousands of years, these slow drips build the spectacular formations we know as stalactites and stalagmites, a type of limestone called travertine built molecule by molecule. Similarly, in hot springs, geothermally heated water brings dissolved minerals, particularly silica, to the surface. As this water cools rapidly upon meeting the cooler air, it can no longer hold its dissolved silica load. The silica precipitates out, forming intricate layered deposits known as siliceous sinter or geyserite around the vent of the spring. These formations are a direct and beautiful record of volcanic activity happening deep below the surface, a testament to the planet's inner heat manifesting itself in a delicate, rocky form. Thus, chemical sedimentary rocks provide a different kind of narrative. They don't speak of the violent journey of fragments, but of the subtle, silent chemistry of water. They tell of changing climates, of evaporating seas, and of the Earth's geothermal heartbeat. From the vast beds of rock salt that lie beneath our feet, to the delicate banded beauty of an agate formed in a volcanic cavity, these rocks are a testament to the creative power of precipitation, transforming an invisible, dissolved world into solid, tangible stone. Our final chapter explores the most intimate connection between geology and biology, the creation of organic sedimentary rocks. These are rocks built not from the fragments of other rocks, nor from the precipitation of minerals alone, but from the accumulated remains of living organisms. They are, honestly, the ultimate proof that life is a geological force, capable of building entire landscapes from its own substance. The story of these rocks is the story of life and death on a planetary scale, repeated over countless millennia. Perhaps the most familiar of these is limestone. Many forms of limestone are born in warm, shallow, sunlit seas, teeming with life. Countless organisms, from microscopic plankton to larger creatures like corals and mollusks, build their shells and skeletons from calcium carbonate extracted from the seawater. When these organisms die, their hard parts sink to the sea floor. Generation after generation, a rain of shells and skeletal fragments accumulates, forming a thick, calcareous ooze. Over geological time, just as with clastic rocks, this organic sediment is buried, compacted by the weight of overlying layers and cemented together, often by more calcite. The result is limestone, a rock made almost entirely from the remains of past life. If you look closely at a piece of fossiliferous limestone, you can often see the individual shells and skeletons perfectly preserved, a tangible connection to a vibrant marine ecosystem that flourished millions of years ago. The Great Pyramids of Giza are built from such rock, a monument of humanity built from a monument of ancient life. A different kind of organic rock tells a story not of the sea, but of the land. Imagine a vast tropical swamp 300 million years ago, long before the dinosaurs. The air is thick with moisture, and giant ferns, mosses, and primitive trees grow in dense profusion. As these plants die, they fall into the stagnant, oxygen-poor water of the swamp. The lack of oxygen prevents them from decaying completely. Instead, the plant matter accumulates layer upon layer, forming a thick, spongy deposit known as peat. As this peat is buried deeper and deeper under new layers of sediment, it is subjected to immense heat and pressure. This geological cooking process drives off water and other volatile compounds, concentrating the carbon. Over millions of years, the soft peat is transformed. First, it becomes lignite, a soft brown coal. With more heat and pressure, it becomes harder bituminous coal, and under the most intense conditions, it is metamorphosed into hard, shiny anthracite. Each lump of coal is a piece of concentrated, fossilized sunshine, the solar energy captured by ancient plants, stored for eons. From the brilliant white cliffs of Dover, composed of the microscopic skeletons of countless coccolithophores, to the dark seams of coal that powered our industrial revolution, organic sedimentary rocks are a profound reminder of the power of life. They are the recycled building blocks of biology, transformed by geological processes into enduring features of our planet's crust. They demonstrate that the lines between the living world and the world of stone are not as clear-cut as we might imagine. Life does not simply live upon the earth, it actively helps to build it. And there you have it, the three main types of sedimentary rocks that shape our planet. We have seen how the fragments of ancient mountains are reborn as clastic rocks like sandstone. We have witnessed the silent chemistry of water crystallizing into chemical rocks like halite. And we have marveled at how the very substance of life itself can be transformed into organic rocks like limestone and coal. Each type, with its unique origin story, contributes to the rich, layered tapestry of our world's geology, a history book open for all to read. These rocks are not merely static objects. They are part of a dynamic, ever-moving cycle. The sandstone on a cliff today may, in 1,000,000 years, be eroded and its grains washed out to sea to form a new layer of sediment. The limestone on the seafloor may be subducted deep into the earth, melted, and reborn as part of a volcano. The story of rock is a story of endless transformation, a narrative that has no final chapter. It is a process that has shaped our world for billions of years and will continue to do so for billions more. The ground beneath our feet is full of such stories, waiting to be discovered. Every pebble, every cliff face, every canyon wall has a tale to tell. I encourage you to look at the world with new eyes, to see the history in the stones around you. The more we understand the processes that have shaped our planet, the more we can appreciate its intricate beauty and its immense, deep history. Keep exploring to uncover more wonders of geology.